Good afternoon, members of the jury, contestant colleagues, and general public. My name is Ruben Romero Maima, and now I am in charge of representing to the Geotechnical Engineering Peruvian Advisory UNI Peru team to explain our solution to this proposed problem. The exposition has this outline, as we can see. So, to start, as a scope, to solve the problem, there are some limitations. For example, the information about the structures and the UCS of the rock mass is null. Also, the excavation has not a real purpose. And there is not financial information about the cost of the tunnel. As objectives, first, we have to determine the minimum depth of a tunnel considering the geotechnical and stability conditions given. Then, carry out a tunnel stability analysis via deterministic and probabilistic methods. And third, conduct a displacement analysis in the contours of the tunnel. And finally, identify the potential risks of the design of the tunnel with the geotechnical and stability conditions. In the problem definition, the problem consists of a geological model in which a horizontal fault is found at 56 meters. This by acting as an impermeable barrier of the water table that is located at the ground surface. That makes it possible to characterize the model in two types of rock, one saturated and the other unsaturated. The rock mass properties such as the unit weight, the cohesion, or the friction angle, among others, are summarized in the first table. And in the same way, the fault properties are summarized in this second table. Then, to solve this problem, two constraints must be considered. The first deals with the acceptance criteria for the geotechnical evaluation, which requires a minimum factor of safety of 1.5 and a maximum probability of failure of 5%. And the second restriction takes into account the depth of the tunnel to be excavated, which cannot be less than 60 meters. The problem requires the estimation of the minimum depth to excavate a circular tunnel of a radius of 3 meters. And also an alternative scenario is asked, considering a second horizontal fault at 67 meters. Okay, in the instability mechanism, we have the characteristics of a weak rock with R less than 50. Also allowing C2 stress the tunnel with depth near the surface. So we consider the instability mechanism is controlled principally by the main discontinuities. And the minor discontinuities are not mentioned in the problem, but it is assumed. It produces an unraveling of logs from the excavation surface. So for the assumptions for our analysis are related for the hydrogeological and the geotechnical model. For the hydrogeological, the water is now present below the first fault and the water table is at the ground surface. For the geotechnical, bidimensional analysis was conducted with numerical methods, in this case, in the software FLAG2D, and the two faults were considered perfectly horizontal and infinite in length. So, for the methodology, we followed three main steps. First, the deterministic approach was conducted analyzing the factor of safety variation in function of the depth. And this is shown as orange curves in the figures. Second, a displacement analysis was conducted for each depth, specifically for the roof of the tunnel. This is shown as a blue curve. And for the roof of the tunnel, this is shown as a green curve. So the zone which the roof displacement tends to be minimum and the factor of safety is greater than 1.5 has the possible answer. In this case, that's zone market, this zone market. And third, a probabilistic approach was conducted. Its variation is shown as a red curve. And in this case, the left zone is discarded because only accomplishes the deterministic acceptance criteria. Then the right zone is the best because it accomplishes both the deterministic and probabilistic analysis. Then for the deterministic approach, all the rock mass and the fault properties are introduced as inputs for each depth on the tunnel. And with it was calculated principally the factor of safety and the roof displacement, as we can see. That is to obtain a factor of safety greater than 1.5 and a minimum roof displacement to get the final design. For the probabilistic approach, all the rock mass and fault properties are introduced considering a normal distribution. With the Stephen method, and then with the Monte Carlo simulation, many probability of failure were calculated for each depth until obtain one value less than 5% to define the final design. So in the stability analysis by the deterministic approach, the factor of safety analyzed should be with the displacement in the roof and the floor, and is realized analysis for each depth. For the deterministic analysis, the factor of safety is always greater than 1.5 in this case, and it could give the first impression that whatever depth could be the answer. But for that, the displacement analysis is carried out. The roof displacement becomes minimum at 62 and 63 meters in this table, and the floor displacement is almost constant. As the results, the roof displacement is always the most critical and is higher than other displacement around the tunnel. As we can see in the model, the higher the displacement are on the roof. And then we can recognize two zones. The zone before the factor of safety reach its maximum value is controlled principally by the fault until this point. So. And after is controlled by the depth. So with analysis, the most adequate depth are the 62 and 63 meters. However, a probabilistic approach must be conducted to improve the credibility of the results. So to validate the previous results, a probabilistic analysis was conducted. First, we followed the response surface method proposed by Stephen to account for the variability in rock mass and fault properties. We assumed a normal distribution for all strength parameters such as cohesion and friction angle by considering their mean and their standard deviation. From the results, we can see that only the cohesion and the friction angle of the rock mass has influence on the resulting factor of safety, while the other parameters like this have not a significant effect which can be observed as horizontal lines. Then we used the Monte Carlo sampling technique or Monte Carlo simulation to run 1,000 iterations for each case and obtain a probability of failure different for each depth. So watching these values, the most appropriate is this that I am showing because the probability of failure is 2.4%, which is lower than the maximum allowed. In the alternative scenario, considering the alternative scenario with a second fault below the tunnel at 67 meters, we can see that the values of the factor of safety and the roof displacement continue being the same. These are the same that the first case. and we can see this variation, but only the floor displacement has increased a few. This variation can be seen here. So the second floor, the second fault principally affects the deformation in the floor and has no effect in the stability conditions. That's probably for the low depth considered, because it is 60 meters in average. Then the probability of failures does not vary. It's continue being the same. So the answer does not change. Okay, for the construction method, as is known, the methods to carry out an excavation are drilling and blasting and TBM. And we can see here the methods to follow a construction method. It depends of the cost, maybe the length to be reached, and also the purpose of the tunnel will have. These aspects are not mentioned in the problem, but three main factors are considered to be able to choose the construction method. The first is the geological factor, since due to the presence of the fault, we are looking for a method that produces the low terrestrial vibration possible. The second factor is the geometric, because since being a circular tunnel, we look for a method that facilitates its execution of a circular geometry. And finally, the support factor that seeks that a chosen method generates a smooth surface that facilitates the process of installing supports in the tunnel. Due to these three principal factors, the TBM was chosen as the construction method more adequate. To finish, as a conclusion, the result of our deterministic and probabilistic analysis, we can state that the minimum depth to which the tunnel could be excavated is 63 meters, having a factor of safety of 2.99 and a probability of failure of 2.4%, and which complies all the geotechnical requirements. And in the case of the alternative scenario, the presence of a second fault below the tunnel is irrelevant for the stability. So the answer continues being 63 meters. So in the case of the potential risks, these are the following. The occurrence of earthquakes, it could generate collapses or fault reactivations. As a monitoring is the selection of a proper support and the installation of accelerographs. Maybe it could be the presence of inundation if the first fault left of acting as a barrier. So it could generate weakening of the cohesion between the rock and collapse. And for the monitoring, we should use piezometric monitoring. Also is the collapse or the entrapment of the TBM. It, as a consequence, could be the stoppage of the construction or higher costs. For monitoring, could be a rock mass characterization, a machinery maintenance, and higher experienced operators. Another is the deformation on the tunnel surface. As a consequence, the instability of collapses, and as a monitoring, the verification of your technical parameters, good lining of the tunnel. For a risk, change of the geological condition and presence of new faults. As a consequence, the instability of the excavation or stoppage of the construction. And to monitoring, a review of the geotechnical holes and improve the reliability of the model. And also the limited information about the structures. It could generate failures around the tunnel and conduct a field mapping campaign for avoid it. So as an knowledge, we want to thank the sponsor of this student competition, Italia Consulting Group, and the organizers, both University of Kentucky and University of Toronto, for hosting this event. We would also like to express our gratitude to our advisor, Mr. Paul Aliaga, for his patience and dedication throughout this process. And last but not least, a special thanks to our families for their continued support during the last weeks of this student contest. So that would be the end of my presentation. Thank you very much for your attention.
Thank you very much, Ruben, for that. Jadis, I leave it for you.
Yeah, just a simple question from me. On your numerical model, how do you decide where to put the lateral boundaries?
The lateral boundaries of is where I am following.
Yeah. Yeah.
We selected a squared model. It was also in the software flexible, and it facilitates the study.
But how do you know they are sufficiently far from the tunnel to not impact the answer?
Yes, the depth is very low. It's in the average of 60 meters, and the stresses or some are very low also, so the effect is less.
Thank you.
Okay.
How realistic do you think that you assume the parameters being statistically independent?
Sorry, that statistically independent?
Well, you assume, for instance, the friction angle and the cohesion are statistically independent. How realistic is this?
Exactly, we considered all the parameters, but this surface method of Stephen was selected also because it can give us an estimation of the importance or the variation or the specifically the effect of each parameter introduced. And in this case, as we can see, principally the parameters that have a curve, line with some slope are has a good influence as the cohesion and the friction angle, and the others that are similar, that horizontal lines, has a minimum effect, or is not significant, the effect to the calculation of the factor of safety or the probability of failure, maybe.
Yeah, but that doesn't answer my question. How realistic is this? Yeah, that's okay. No. Why don't you, Lauren, why don't you ask a question?
I have one question. It's unclear to me how your analysis included an assessment of the slippage along the faults. Can you explain that?
The sleepings along the fault?
Yes, that was one of the criterions of this problem statement.
How this we selected this method to because we saw in the bibliography that in the case of if the rock is weak and the low in situ stress is low, the situ stress is low, the instability would be by unraveling of block from the excavation surface. But we assumed that exists minor discontinuities as in the image, but in the problem we only had the horizontal line, for example.
Okay.
Okay.
Right. Thank you, Ruben. Thank you to the GEPA team for presenting. I leave the judges with a couple of minutes to enter their scores by the time we call in on the next team.